Um, then we introduced the notion of DFT, discrete Fourier transform, and we related DFT to both discrete Fourier series and discrete time Fourier transform. So the relationship was pretty straightforward. Um, if you take a DTFT of an endpoint sequence, and if you take an endpoint DFT of an endpoint sequence, then DFT is just n equally spaced samples of the DTFT. Also, there's another way of defining DFT and relating it to discrete Fourier series, and that is you start with a finite length sequence endpoint, and you want to compute its endpoint DFT. What you do is you make it periodic with period n. You compute its discrete Fourier series. Then you take one period of discrete Fourier series, and that's also DFT. So in some sense, DFT is related to both of these in a fairly straightforward way. Okay? And we sort of ended last time's lecture with a picture like this, where here's DFT, and the input to the DFT box is an x of n, where n is an integer. It's a aperiodic, that means non-periodic, finite extent sequence. Out comes x of k, an array of n numbers. If this is n points long, there comes n numbers. And one of the things that I talked about quite a bit was DFT is an important transform because it's the only transform that we ever cover in any of these courses that's computable. It takes an array of numbers as input, an endpoint array of numbers, and it produces an array of numbers as output. Endpoint in, endpoint out. In contrast, when I talk about DTFT, discrete time Fourier transform, you give it a sequence, and what comes is a function of a real variable omega. Also, DFS takes a periodic sequence and comes up with a periodic sequence. So this picture sort of summarizes DAO. It shows the relationship between DFT and DFS. It also shows the relationship between DFT and DTFT. So what I like to do in today's lecture is first start talking about padding sequences, finite length sequences of some length with some zeros, making the length longer, and talking about taking Fourier DFT of the longer sequence. In other words, I'm going to talk about not only endpoint DFT of an endpoint sequence, but also n prime point DFT of an endpoint sequence, and I'll explain what I mean by that, where n prime is some larger number than n. And then I'll go through a little thought experiment to show that to go a little bit deeper into the relationship between DTFT and DFT. And the purpose of it will become clear, hopefully, shortly thereafter, when we start talking about using DFT to do convolution. Okay? So that's sort of the outline of today's lecture, if you will. Any questions or comments or issues? Okay, so let me get going. So the topic of our discussion is DFT, again, which is just discrete Fourier transform. Okay. So what we talked about last time was that if you have a finite length endpoint sequence x of n with n non-zero values, then its DFT is given by x of k, which is summation from n equals 0 to n minus 1 x of n e to the minus j 2 pi nk over n. That's for k between n and 0, and it's 0 otherwise. That means other values of k. Okay? And what we talked about before was that whenever you have an endpoint sequence, you can take its endpoint DFT to get n numbers out. So the picture that you have is n numbers into the DFT box and n numbers out. Okay. So what I'm proposing in this lecture is that you could take, it's possible to start with a finite length endpoint sequence with n non-zero values, and it's possible to pad it with a bunch of zeros. So it's possible to pad an endpoint sequence with n non-zero values to something like, I don't know, endpoints, i.e. padded with m minus n additional zeros. And if you do that, then it's indeed possible to talk about the DFT of the resulting endpoint sequence. Possible to talk about the DFT of the endpoint sequence. So what do I mean by that? Well, pictorially, what's really happening is here's the idea. So 0 all the way to n minus 1. This is x of n. So what I'm talking about is padding this sequence with a bunch of zeros all the way, so I get a total of endpoints. Okay? And so effectively, I can take an endpoint, so I can either take an endpoint DFT of x of n, or I can take endpoint DFT of x of n. I can take endpoint DFT of x of n. And what that would be given by this expression. It will be again x of k summation from n equals 0 to m minus 1 of x of n. And what would be the exponential that we put? E to the minus j 2 pi nk over m. And this is for k in between m and 0, or it's 0 otherwise. Okay? So on the surface, you might think that this DFT is the same as the endpoint DFT. Why? You would say, oh, these additional terms that you're having in this summation as compared to the endpoint DFT, they're just 0, because these are all zeros that I padded. So x of n plus 1, x of capital N plus 2, they're all 0, so this summation doesn't change, so it must be the same as that. But that's not really true, because the exponential for the non-zero terms of x of n, the exponential I'm multiplying with are different in these two cases. This is e to the minus j 2 pi nk over capital N. This is e to the minus j 2 pi nk over capital M. Okay? So in this case, what's really happening, this is my DFT box, endpoints go in, and endpoints come out. And I can refer to this thing as the endpoint DFT of that same sequence. And the reason it makes sense, even though the original sequence only had n points, the reason it makes sense is because you can always pad it with enough zeros to make it an n-point sequence and get done and over with. So just to make things a little bit more concrete, and I'll explain to you why all of this is important. I'm not trying to torture you in a sadistic way or anything like that. It becomes important when we talk about using DFT to do linear convolution. So as an example, suppose I have a sequence x of n that is 0, that has the following values at these indices. Okay, so it's really a 4-point sequence. Okay, and I can take a 4-point DFT of x of n, and that would be summation from n equals 0 to 3 of x of n e to the minus j 2 pi n k over 4. Okay, or I can take a 5-point DFT of x of n, and that would be summation from n equals 0 to 4 of x of n e to the minus j 2 pi n k over 5. Okay, or I can take a 1,000-point DFT of x of n. And what I would get then is n equals 0 to 999 x of n e to the minus j 2 pi n k over 1,000. And in the back of your mind, you might say, well, how are these things related to each other? Let's for completeness, let's also talk about the 8-point DFT of x of n. That would be summation n equals 0 to 7 x of n e to the minus j 2 pi n k over 8. So just off the top of your head, how would, so this is an array of 8 numbers, this is an array of 4 numbers, this is an array of 1,000 numbers. Okay, no, I'm sorry, this is 5, sorry. This is an array of 4 numbers. In other words, the x of k, I can compute k here for k equals 0, 1, 2, 3. Here I can compute it 0, 1, 2, 3, 4. Here I can compute it for k equals 0 all the way to 999. And here, 0, 1, 2, 3, 4, 5, 6, 7. So I might say, how is, for example, these 8 numbers here related to the 4 numbers here? Can anybody guess? Based on inspection of these two expressions.
The even.
Okay, somebody picked up the microphone.
The 8 was an upsampled version of the.
And what do we mean exactly by that?
Get the DTFT. Split at twice the rate of the
Right.
original.
Right. So the way to understand the relationship between these two guys is to relate back to what we knew on DTFT. The DFT of any sequence is always its equally spaced samples of its DTFT. And so this discussion I'm having essentially boils down to the following thing. I start with x of n, and it's an n-point sequence. Then I pad it with m minus n zeros, and I get a new x of n that's m-point. And then I call it still x of n, and then I take its m-point DFT, and I get an m-point sequence. So x of n corresponds to some sort of x of omega, 0, 2 pi, something that's periodic. For now, I'm just showing one period of it. And if I start with x of n and take its n points, suppose x of n is just an n-point sequence. If I take its n-point DFT and I get n numbers out, then I get those numbers corresponds to n equally spaced points on my x of omega, 0, 1, 2, 3, 4, 5, 6, 7, 8 in this case, right? In fact, one of them have to be add 0, so let's not put that. Now, if I start with x of n and take 2n point, for example, DFT of it, and I get 2n numbers out, then these 2n numbers, and remember, again, x of n is n point sequence in order for me to take 2 endpoint DFT of it, I've essentially padded it with n extra zeros, right? Everybody follows that, right? So when I have a 5-point sequence and I talk about this 10-point DFT, I'm talking about padding it with 5 more zeros. If I have a 5-point sequence and I talk about a 1,000-point DFT of it, I'm padding it with 995 zeros, right? That's the general terminology we're talking about. But here I'm talking about an n-point sequence. I pad it with n more zeros. I get 2n, and I take the 2n-point DFT, and I get 2n numbers. How is that related to x of omega? Well, it's samples of x of omega at 2n equally spaced points. So it'd be here, it'd be here, it'd be here, it'd be here, 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 here. Okay? So it's the same period 0 to pi, but the same continuous function x of omega, but I'm sampling it at twice the rate. And because this is 2n, and this is n, 1 out of every 2 samples of these two guys coincide with each other, fall right on top of each other. Okay? So in effect, if I wanted to represent my n-point sequence x of n minimally in the Fourier domain, because it has n points, I really need to have I really only need to take n-point DFT of it. And n-point in the frequency domain are enough for me to uniquely reconstruct x of n back. How do I do that unique reconstruction? It's called inverse DFT, right? We saw the equation for it last time. So if I start with an n-point sequence, and I take its n-point DFT, and I get n numbers out, that's enough to represent the sequence. Now, what if I start with an n-point sequence with n non-zero values and pad it with n additional zeros, and I take 2 n-point DFT of it, then I get 2n numbers. Well, can I still recover my original sequence back? Sure. Take a 2 n-point inverse DFT, and I get a 2 n-point sequence, and of that 2 n-point sequence, the latter half of it is all zeros, and the first half is all the non-zero values that was in x of n, right? So all of those things that we talked about, the relationship with DTFT, and all of those things holds true. Now, what if I asked you a trick question and I said, I have 2n numbers. I start with an x of n, which has n non-zero values. I pad it with n zeros. I take a 2 n-point DFT of it. I get 2n numbers. But I only have a box that does inverse DFT for n-point sequences and not 2 n-point sequences. How would I get back my original sequence x of n? There's no zeros here. This is 2n samples of this. Downsample, remove the ones in between, get n points, and then take inverse DFT. All right? So this is sort of roughly the relationship between the conclusion I want you to get out of this story is that even if you start with an n-point sequence with n non-zero values, it's kosher and it's okay and it's legal to take n prime point DFT of it, where n prime is larger than n, or m point DFT of it, where m is larger than n. And essentially all you're doing is you're padding it with extra zeros to make it m point long, and then taking its DFT. And in the process of doing that, all you're really doing is you're sampling its DFT at finer points, right? And one of the questions you might ask yourself is, what is the minimum number of samples of the DTFT that's needed to recover x of n? And what do you think the answer is? If x of n is an n-point sequence, what's the minimum number of samples of the DTFT, equally spaced samples of the DTFT that you can get away with recovering x of n? It's just n. But in the case of 2n, yeah, I have these extra samples in between, here, 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 but they're not needed. Okay? So in some sense, in this case, we're oversampling our DTFT. We're oversampling our Fourier transform. And just as a side comment, even if the samples of your DTFT are not equally spaced, in other words, you don't have DFT of a sequence, but they're non-equally spaced, this is a side comment, you can still recover x of n. And can anybody think of an algorithm that would do that? Suppose that I have this x of omega, again, between 0 and 2 pi, and I know it corresponds to dTFT of an n-point sequence, but instead of having n equally spaced points, I have it at n non-equally spaced points. Can anybody think of an algorithm that would enable me to recover x of n? Yeah. Well, they're really random and non-uniform. Exactly. Solving a linear system of equations. Is that what you meant? So suppose that this is a side comment. It's not really related to the main topic of today's lecture, but it's interesting. Suppose we have non-uniform samples of x of omega at n points, non-uniform, there's not equal. And suppose we know that x of omega is a dTFT of an n-point sequence. Then what? Then can I recover x of n? And the answer is yes, by solving a linear system of equations. And how can we come up with this linear system of equations? You just go back to the definition of x of omega. You say x of omega is the summation of x of n e to the minus j omega n. And I know x of omega sub I know x of omega sub I for I ranging from 0 all the way to n minus 1. So these are the frequencies, non-uniform frequency samples for which I know x of omega. Then they're equal to x of n, summation from n equals 0 to n minus 1, e to the minus j omega sub I times n. Then how do I recover? How do I end up recovering what x of n is? Well, it's a linear system of equations because I make an array of x of omega 0, x of omega 1, da 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 da, all the way x of omega n minus 1. That's my left-hand side. And then I have a matrix here, and then here's my unknowns, little x of 0, x of 1, all the way to x of n minus 1. So this is the unknown. This is known because this is the known non-uniform samples that we're after. And then here I have a matrix. And what are the elements of that matrix? Well, for every value of omega I, it's the values here. So let's say I'm talking about omega 0. So it would be x of 0 times e to the minus j omega 0 times 0. So that would be 1. E to the minus j omega 0 times 1. E to the minus j omega 0 times 2. Da 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 da. E to the minus j omega 0 times n minus 1. That would be the row, the first row of the matrix. And then I can come up with the second row, the third row. And the last one would be for omega sub n minus 1. So it would be e to the minus j omega n minus 1 times 0. E to the minus j omega sub n minus 1 times 1. Da 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 da, all the way e to the minus j omega sub n minus 1 times n minus 1. So this would be the structure of our matrix. So we know this one, that's the known non-uniform samples, that's our unknown, and we know this matrix. And the reason we know this matrix is because we know these frequencies, these non-uniform sampling frequencies, omega 0, omega 1, all the way to omega n, and so we can solve the linear system of equations. And this matrix, this is an n-point array, n-point vector, this is an n-point vector, and this is an n by n matrix. There's only a danger of one thing going wrong. And what's that thing? That this matrix could be singular. And under what conditions can it be singular, or can it be singular? It turns out this matrix has a particular name. Does anybody know what it's called? Pardon? Louder, I can't hear. It's called Van der Monde matrix, right? And any matrix which is, and it's essentially a number like the first number here, let's call e to the minus j omega naught. Let's call it a. So it's a to the 0, a to the 1, a to the 2, a to the 3, all the way a to the n minus 1. Let's call e to the minus j omega 1 b. The second row is b to the power of 0, b to the power of 1, b to the power of 3, etc., all the way b to the power of n minus 1. So each row of this has this structure, and that's called the Vandermonde matrix. And you can show in math that Vandermonde matrices always have non-zero determinant. They're always non-singular. Unless what happens? That's a pretty obvious thing. Under what condition will the thing become singular? Unless two rows are the same, and that means omega 0 is equal to omega 1, in which case you've sampled the same frequency twice. Okay, which is a bad thing. You want to sample every frequency. You don't want to have two values for the same frequency. So that's the extreme. When two rows are identical, the thing becomes singular. So even though, strictly speaking, as long as omega I is not equal to omega j, this matrix is non-singular. Remember, when you solve a linear system of equation, there's two condition numbers. There's a condition number of the problem and then the condition number of the algorithm you use to solve it. And let's say we're so smart, we know all of our algorithms so well, we're going to use the most stable algorithm, let's say QR decomposition. So let's put that aside. But the condition number of the problem is what? In the case of solving AX equals B, has to do with the condition number of the matrix. So this is matrix A, this is X, and this is B, right? So I'm solving AX equals B, and this matrix A has a thing called condition number. And what's the condition number of a matrix? I think we went over that at the beginning of the class. It's the ratio between its largest singular value over the smallest singular value. So even though I apply a fancy algorithm, and even though the matrix, strictly speaking, could be non-singular, because it has all different omega i's in each of the rows, the problem could become ill-conditioned if two omegas are really close to each other. And how does it become ill-conditioned? This matrix becomes ill-conditioned. In other words, its condition number becomes large. In other words, the ratio between its largest singular value and smallest singular value becomes large, makes the matrix ill-conditioned. And what does that mean? It means that the problem is ill-conditioned and you have a hard time figuring out what the values of the input are. So intuitively, does that make any sense? Yeah, it does. What it says is that even though you have non-uniform samples of these guys, as long as two samples are not extremely close to each other, you have a good shot of recovering X. And when the samples become really close, in the limit, when they become so close that they're almost the same, then this matrix hits singularity and it becomes non-singular. But what I'm trying to convey to you is that most times in computational problems, it's not a binary thing. Is the matrix singular or non-singular? A lot of times there's this gray region. Matrices could approach singularity without exactly being singular. And the way it manifests itself in your calculation is for the condition number of your problems being very large. And in that case, if these samples are God-given and you can't really change where they came from, the only solution you can resort to, if you have an ill-conditioned problem or an ill-conditioned matrix, is to throw a lot of precision to your problem. Use double precision with 64 bits of precision rather than 32, rather than 16. If you got 128-bit machines, throw 128 bits. That way the round-off error makes this matrix not become singular so rapidly. Okay? So one other comment I'd like to make is all of what I just talked about is not science fiction. There's a lot of applications where you get non-uniform samples of a Fourier transform of something. Can anybody think of one?
X-ray crystallography.
Yeah, X-ray crystallography is one example. And have you worked on that problem actually yourself? Or you've heard about it? Pardon? You have a friend. Okay, very good. And
what if your samples are all packed, in the first half of the interval?
It should be able to recover it.
But you don't know what it's doing in the set. I mean, it could be doing anything. And
no, it can't. You know why it can't? Because there's only n unknowns. It can't be doing anything. So as long as you have n samples as long as this van der Waals matrix is non-singular, and it won't be a well-conditioned problem. That's for sure is true. So if I had infinite precision, I would have done it. But there's a theory, and then there's a practical aspect. So the theory says, as long as the omega i's are distinct from each other, this matrix is non-singular, you should be able to recover X of n. Practice, the matrix becomes close to singular or ill-conditioned. So let's come back to this application. In MRI, magnetic resonance imaging, that's one application where you sample the Fourier domain. In fact, you sample two-dimensional Fourier domain, omega 1 and omega 2. And in traditional sampling of MRI, what they do is first they apply a magnetic field, let's say that's parallel to the ground, and it selects a slice of my body. For example, it selects my, I don't know, L4, L5 disc. That's the disc that they think there might be something wrong. And then they apply a series of pulses, and as they apply pulses, essentially what they're doing is they're obtaining samples of the hydrogen density of the Fourier transform of that region. So these are n samples, and then another click, and then n more samples of the next one, and then n more samples. So in this case, they do it in a regular way, but sometimes in order to get it faster, they do spiral sampling. So in that case, in order to compute the inverse 2D DFT of it, first you have to regrid or reinterpolate from the spiral sample into rectangular, and then take inverse DFT. Or just solve that linear system of equations I just talked to you about, and then compute the values. So coming back, I have one more comment to say about this thing, about the fact that if these are non-uniform, you plug it in, and if the two samples are very close to each other, then this matrix could become singular. Now, what is the best possibility for this matrix? What is the best condition number anything could have? A condition number is the ratio between largest singular vector value over smallest singular value. Okay? What is the small? So a really badly conditioned matrix that results in a bad condition problem is one where the condition number is large. It's 1 billion, it's 1 million, it's 1,000 billion, or trillion, whatever. What's the smallest the condition number can get? No, then the ratio between largest and smallest singular value. I have n singular values. I rank order them from the largest to the smallest. 1. So the smallest the condition number that become, the best condition problem that we all dream of is when your condition number is 1. And for God's sake, what sampling of the frequency domain will result in condition number of 1? What matrix has condition number of 1? Has when you do equal spacing, which is exactly the uniform samples, which is exactly inverse DFT, the inverse DFT matrix is the one that has condition number of 1. So that's the easiest, best condition sort of a way of computing the samples, the samples of your sequence. So other examples where you get non-uniform samples besides, so examples that you get non-uniform samples in frequency domain. So one of them was, you said X-ray crystallography. That's very true. And what application is X-ray crystallography, in your opinion, used the most in?
Studying the magnetic interactions of magnetism.
Magnetic interactions of what?
Just how magnetism works, kind of.
Okay. I had heard it used in like drug design. You use it.
It's widely used in biology.
Yeah. So widely used in biology/drug design. Another one is MRI. We just talked about. Another one is what? Radar. You get Fourier transform of the topography of the thing that you're looking at. Another one is radio astronomy, for example. Many times you get non-uniform samples or something like that. What else? Tomography. If you take E225B, not next semester, but spring of 2005, you learn all about tomography. In tomography, where that name is like X-rays. you get either polar samples, that means equally spaced samples like that in a circle, or you get other kinds of samples, and then you have to, from this, you have to recover your n by n sequence in 2D, and you can either solve an inverse system of equation, linear system of equations to find the values of sample, or from these you can reinterpolate and compute the values on a regular grid, and then once you have it on a regular grid, a regular inverse DFT would do the job and gives you the samples back. Okay. Okay, so that was a bit of a detour, but I think hopefully it was interesting. So, so coming back to this discussion, so what I want to do, having talked about this DFT, having talked about this concept of taking a larger number of point DFT of a sequence. You got an endpoint sequence, you can take 2 endpoint DFT of it, 5 endpoint, 10 endpoint, whatever you like. Next, I want to do a thought experiment, and this becomes handy when we deal with convolution properties again. And the thought experiment is as follows. I start with y of n, a sequence y of n that could be either infinite extent or finite extent. And suppose that I compute y of omega, which is the DTFT y of n. Okay, and then I sample y of omega at n equally spaced point. In other words, y of omega evaluated at omega equals 2 pi k over n is equal to x of k. And this thing is now an n-point sequence. So y of n, I'm not making any claim how many point sequence it was. If it was finite extent, it was n point, m point, or maybe it was even an infinite extent sequence. But essentially, and then what I do is I take inverse DTFT of x of k, and I get a new sequence, x of n, and because this is an n-point sequence, this ends up being also an n-point sequence. So effectively what's happening is in the z domain, this is y of omega. I have a y of omega, which is y of z evaluated on the unit circle, and I'm just sampling it arbitrarily at n equally spaced points. And I don't even know whether the original sequence, I don't even know this DTFT, whether it corresponded to an n-point sequence, the 5-point sequence, a 2 n-point sequence. I just don't know that. It could have been a 1,000-point sequence. It could have been a 2-point sequence. But now I come ahead and I go ahead and I sample it, let's say, at 16 points. The question, and I get a new, and I sample it, take an inverse DFT of it, get a 16-point sequence in time domain, and I ask myself, how is that 16-point sequence related to that original sequence? Y. Remember, Y is the thing that could be 2 point, 1,000,000 point, 1,000 point. How is that 16 point related to the 2-point sequence? Okay. And I don't expect you to know the answer. I'm going to derive this. But before I do that, let's develop a little bit of an intuition. If the length of y of n was exactly n points, in this case 16 points, what would be the relationship between x and y? They'll be identical, right? I start with a 16-point sequence, compute the 16. I compute this DTFT and then sample it at 16 equal space point. Take inverse DFT, I get the x of n. That is the definition of DFT. DFT of a 16-point sequence is 16 equally spaced samples of it, right? Let me ask you another question. What happens if n, in this case, is larger than the number of non-zero points in y of n. In other words, y of n was a 4-point sequence, and I computed this DTFT, and then I sampled it at 16 points, and then I took a 16-point inverse DFT of those samples, and I got a 16-point time domain sequence. How would y of n and x of n be related to each other? Right. The first 4 points of y of n is the same as x of n, and the remaining ones are 0. 12 of them would be 0. And is that clear to everybody? That's clear because of this discussion we went through, right? This discussion that we just went through, right? So at least in those two cases, we know the answer. What happens if the length of, the only thing that we don't really know the answer is, what happens if the length of y of n is larger than n? In other words, y of n was a 32-point sequence. We took his DTFT, but now, even it's a 32-point sequence, we sampled this DTFT at 16 points and took an inverse. What would we get then? How would y of n be related to x of n? What does it mean we get aliasing?
So, the different periods overlap
Mm-hmm.
with each other, so some samples get lost and we don't know.
Right. So what happens then, and it shouldn't be extremely clear, I'll show it to you in the derivation, but what you get then, x of n is the aliased version of y of n. It's a periodic version of y of n with period 16, with period n. So you start with y of n, which is 32 points, but you repeat it every 16 points. You make a periodic sequence out of it that way. And one period of that would be x of n. That's the answer, but let's just show that just so that you're convinced and you see why that's true. Okay? So the answer, I'll write down the answer before I derive it. The answer is periodicize, and in fact, you don't have to consider these three cases. What if the length of y of n is smaller than x of n? What if the length is the same? What if it's bigger? All of them can be generalized with this answer, which is periodicize y of n with period n. In other words, compute w of n, which is just summation from k minus infinity to plus infinity y of n plus kn. Extract one period. In other words, x of n is w of n times r sub n of n. That's it. That is the answer.
What if y of n is infinity? Because it is infinite.
You can still alias it over. You have something that's infinitely long, you can repeat it every n period, and then add them all up, and you still get a periodic sequence with period n. No matter what sequence you start with, finite length, infinite length, it doesn't matter what it is. If you periodicize it with period n, and replicate it like that, this thing is going to be a periodic sequence of period n, and you just take one period of it. Okay? So now that I gave you the answer, let me try to convince you that that is it. And remember, this answer, by the way, works for all cases. When the length of y of n is smaller than x of n, when you make this thing periodic, you have a bunch of zeros in between, no aliasing, and the answer is the same as what we would have gotten before. So you don't really have to consider three cases. Yeah? Okay. So let's just do a formal derivation of or proof of this thing so that you're all convinced. So how do I do that? Well, staring at this thing here, I got to relate x to y. So let me just work my way up. And how do I work my way up? I'm going to write down the expression for x of n. Well, x of n, so this is proof. X of n is inverse DFT of x of k. So what is it? The definition is it's equal to 1 over n summation from k equals 0 to n minus 1 of x of k e to the minus j 2 pi nk over n for n smaller than n and 0, and it's 0 otherwise. Okay, that is because I'm taking an n-point inverse DFT of x of k, that's how x of n and x of k are related to each other. Now I'm going to relate x of k to y of omega because that's how they're related to each other. Work my way backwards. So now, doing that, what do I get? X of n is equal to 1 over n summation from k equals 0 to n minus 1. And now instead of x of k, I'm going to put this thing. Y of omega sampled at y, omega equals 2 pi k over n. So how do I do that? Well, what is y of omega? Summation over m of y of m e to the minus j omega m. But I want to replace the omegas with 2 pi k over n. So it's 2 pi k over n. So in this step, I've combined this together with the basic definition of y of omega. And the exponential just follows through, e to the minus j 2 pi n k over n. And the reason I use this dummy index m, because I already got the index n going and I don't want to get them confused. This is just a dummy index anyway. And notice, I am not putting any restriction of what this range of m is, whether it's from 0 to n, 0 to 2n, minus infinity to plus infinity. It could be anything. We don't know that. So I'm deriving this for a general way of y. Yeah.
Isn't the exponential positive in this equation?
Yes. Thank you. Thank you. Yeah, thank you. And then, so this is for n in between n and 0, and it's 0 otherwise. And then what? So now I have two summations, and what I'm going to do is change the order of them. The summation is summation from m minus infinity to plus infinity of y of m, k equals 0 to n minus 1. I'm changing the order of these guys. And I'm keeping all the exponentials now here that are k dependent. So y of m is not k dependent, so it's outside this summation that depends on k. The remaining of pieces are all k dependent, so they have to stay inside the summation that has k. So it'll be e to the minus j 2 pi k m minus n over n. Again, for n smaller than n, and 0, and then 0 otherwise. Okay. Question?
Are we missing the 1 over n factor?
Oh, I forgot again. Yeah. And I'm going to actually, so what is this thing? What's this thing? That's the same, that is this summation we did in the last lecture. There's a thing called equation.train. If you go back, let me see if I can find it in my notes. Yeah, it's right here. This was equation.train. It says 1 over n summation of k equals 0 to n minus 1 on the Barton exponentials is this delta. Remember, we named that equation train. So if I bring the 1 over n here instead of here and compare these two things, given that this is equal to delta, we can compare these two things. One of them, both of them are 1 over n. Both of them are k equals 0 to n minus 1, e to the minus j, 2 pi k, m minus n over n, etc. So if this is equal to this function, this thing is going to be delta of, instead of n, m minus n, or rather n minus m. It really doesn't make any difference. So if, as long as I replace this n with n minus m, I'm all done, right? So let's do that. So x of n, so this thing is equal to, from last time, the summation over delta of n minus m plus Rn, for R ranging from minus infinity to plus infinity. Okay? So I'm going to do a little notation. I'm going to call f of n to be just the basic summation of R minus infinity to infinity of delta of n plus Rn. If that's what f of n is, then this blah here is nothing but f of n minus m, right? If I call this f of n, then this thing is just f of n minus m. So f of these two things are equal to each other. So having done all of that, then what do I get? X of n is equal to the summation from m minus infinity to plus infinity of y of m and f of n minus m, where f is this function. Again, for n smaller than n 0 or 0 otherwise. And what is this thing? That's the convolution of y with this train of delta functions, right? This equation here is just nothing but linear convolution of y with this train of delta function. So what happens if I have a periodic train of delta functions and convolve with y of m? Y of n just gets repeated with period of this delta function, which is n. So this is nothing but, let's just write it out. If you can zoom up just a little bit, yeah. So this is nothing but, again, R from minus infinity to plus infinity, y of n plus Rn, for n in between n and 0, and it's 0 otherwise. Done. So x of n is just one period of replicated version of y, or alias version of y. And what do I mean by alias version of y? I start with y and I periodically repeat it with period n, just like I said before. And I take one period, and that's x, which is what I said at the very beginning. So the whole thing hinges upon a bunch of substitutions and applying the equation .train that we came about last time. Did everybody follow this last step? This is a convolution. I'm convolving a train of delta functions over y, and all that does is it replicates y with a period of train in that period. So what is the upshot of all these things, all this thought experiment? It is this. It's the fact that if I start with y, it doesn't matter finite or infinite. It has some DTFT. I sample it at endpoints, take inverse DFT of those endpoints, get x of n. How is that x of n related to y of n? Because I sample it at endpoints, the way these two are related is I replicate y of n with period n, take one period, alias it, in other words, take one period, and that's x. And if the number of points in y of n was smaller than x of n to begin with, that replicating function doesn't introduce any aliasing, and we're done. That's the easy case. And if the length of y of n is larger than n, the aliasing will make things spill over. So let's do that pictorially. So how is this function, how does this function look like for different values of x? Well, if suppose that y of n, for example, was a 1,000-point sequence. It went all the way to 0 to a 1,001-point sequence. And suppose n was 800. So how does this function look like? Well, what do I mean it's this periodic aliased version? Well, that means that I start with that, and with period 800, I repeat it. So this is 800. This is 1600. This is It comes all the way to 200. That's the previous one. So I alias it like that, and I just take one period. Remember, x of n is an inverse DFT of something. An inverse DFT of something, anything in the universe, is always true for the first n values, for n equals 0 to that number. So 0 to 800. So that is, after I do all the aliasing, so add this value to that value, add this value to this value, this one to that one, this one to that one, etc. This first 800 numbers is the x of n that we're after. So this is x of n. And can you all convince yourself that when I replicate this thing, the resulting thing is a periodic sequence? It's always this blah added in this thing, this blah added here, this blah added here. It is periodic. Okay? Alternatively, if even though this is 1,000 points, if I did n equals, I don't know, 1,200, how would this thing look like? Well, I'd periodically repeat y of n with period 1,200. So it'd go from here to 1,000. But then there'll be nothing, and I'll do it here and some more, 2,200, then here and some more, but it ends at minus 200. So then they won't overlap with each other. And I pick the first 1,200, so that'll be my x of n. So it'll be y of n intact from the original, plus a bunch of zeros, which are pretty benign. Okay? So these are sort of the two cases. In this case, we oversampled the DTFT of y of n. Y of n was 1,000 point. We sampled it at 1,200. In this case, we undersampled. It was 1,000. We took 800. So what's the morale of sort of this story? What can we say about this story? The one thing you want to walk away, the takeaway is that if we sample y of omega at a sampling rate that's larger than the number of non-zero samples of y, we should be able to get it back. That's sort of what the thing says. So the thing is to get y of n back precisely, we need to sample its DTFT, i.e. y of omega, at a higher rate than the number of non-zero points in y of n. So if y of n had 1,000 non-zero points, we got to sample it as 1,000 or higher. And if y of n had, if you sample it at a lower rate, you get this aliasing, which is the dual of aliasing that you would have gotten in frequency domain when you deal with sampling. Question?
So, yes, this makes sense, but if you just have y of omega and you don't know y of n, then...
You don't know how many samples it is.
Right, if you don't have any information about y of n besides y of omega, do you just use a lot of points in y of omega and just...
Well, a lot of times you don't have... The application dictates how many samples of y of omega you can get. So if your application only gives you 4, then you're going to get a 4-point sequence. So in real life, if you don't really know how long y of n is, but let's say you can put detectors that can sample this at any rate you want it, 1,000, 2,000. So how would you decide in practice how to use this thing? And the answer is, for some typical examples, you sampled it as 1,000 point. And remember, just like no real-life signal is strictly band-limited, no sequence is strictly time-limited either, right? So you do it at 1,000 point. You say, well, it's almost very close to 0 if I do 1,000. If I do at 2,000, it gets even closer to 0. So it becomes a matter of practical design. Shall I really be go out of my way to prevent aliasing and get my sequence, or shall I just, stop at 1,000, keep the complexity of my system to a small number of 1,000, and get the 1,000 most important samples of the sequence I'm after, if you will. So it's a lot of practical sort of design comes into it. I went over this because I wanted to show sort of the duality between aliasing in time and in frequency domain, right? Yeah.
I'm wondering whether this statement is correct because think of if we have yn is 111,011, then we have 51 and 10. 10 is inserted between the ones, so we have we need 6 samples to recover yn, or we need 5 samples.
I didn't catch your example. So what's y of n?
Yn is 31, 111, 011. It is 6 taps.
Mm-hmm.
And with 10 inserted between 5 ones, just 6 taps.
Yeah.
So we need a samples of DTFT 6 samples to recover yn.
Yeah.
But according to this statement, we need only.
Or when I
5.
say non-zero, I mean contiguous non-zero. I don't mean, number of contiguous. That's what I mean. I mean that we don't care about the padded zeros at the end. That's all I'm trying. Okay. Okay. So and again, this, please remember this thought experiment because we're going to use it on Friday. So maybe if you're lucky, maybe we even hit it today. But what I want to talk about next is some properties. I want to switch gears and I want to talk about properties of DFT. And in particular, I don't want to go through properties that are boring and you've seen a million times, but I'm going to go over properties that are tricky. But actually, these properties are damn important because every time you play with MATLAB, you're dealing with DFT. And if you don't know, DFT, as I said earlier, is the only computable transform you will ever encounter in these signals and systems courses. Everything else has functions of real variables and complex variables and non-computable and just useless. As many times comes to computation. They're important conceptually, but from a computational point of view, they're not. But here's some properties of DFTs that trip a lot of people. Okay. So the first one that I want to talk about is a shift property. Okay, so if I have an x of n, that's n-point sequence, and I take its DFT, and it gives me x of k, what is the DFT of x minus x naught? Or what happens if I take the inverse DFT of x of k e to the minus j 2 pi n naught over k times k over n? So the question is, I don't know this, but if I just multiply in the frequency domain by this exponential, what happens to my sequence? Does it get shifted like this?
No.
It doesn't get shifted like this. Don't tell me the answer yet. Why this is not a correct answer? I need more of that. Why is it that if I apply inverse DFT to this blah, why is it that it can't be this blah here? It's circular shift, but why?
Because the exponential applies periodic, and if you apply, if you increase the n naught such that the answer is the same thing modulo n, the left-hand side.
It's much simpler than that. Because what's the definition of forward DFT and inverse DFT? The forward DFT, you need an n-point sequence that's valid between 0 and n minus 1. You plug it into this, and you get that. And it's 0 for all other values of k. That's the only n-point DFT that's valid. Inverse DFT of anything in the universe. If I have an n-point sequence and I take inverse DFT of it, it only results in n non-zero points for the indices between 0 and n, and it's 0 otherwise. I don't care what that thing is that I'm taking this inverse DFT. It's only non-zero for the first n values of x of n, and it's 0 all the other time. So what I'm asking you is, I start with, this is an n-point sequence, and it's valid for k between n and 0. Good. Then I multiply by this exponential. This is another n-point sequence, and it's valid for k between n and 0. As I said, anything that you take its inverse DFT, if I take the inverse DFT of this guy, I want to get something that's, the answer here should only have non-zero for the first n points. So x of n minus n naught is out the door, because this has shifted this thing. The region of support of this guy used to be between 0 and n minus 1. And now if I do this, it's going to get shifted, and that's off. So some of you have said it's a circular shift, but can anybody say why it's a circular endpoint shift of this thing? And circular shift means you start with x of n, and if I shift, let's say it's 0, 1, 2, 3, okay? And if I shift it by 1, that means this becomes 0, 1, 2, and then the 3 falls off and wraps around here, wraps back here. That's called the circular shift of this. So if n naught was equal to 1, this would be x of n minus n naught circular shifted. But why is it that it's this? Can anybody come up with a quick argument? Yeah.
Essentially, we do IDFT because first we periodicize the x of k, then the IDFS, then take one period.
Exactly. Right on. So this is why it paid off for us to have gone through the DFS route. None of this breaks down when you deal with DFS. And there is a relationship between DFT and DFS. And what is it? Every time I want to compute inverse DFT of something, I first make it periodic, then I take inverse discrete Fourier series, then I take one period of it. And if I follow suit, that was the relationship between DFT and DFS. And if I follow suit and do all the things I just said, going from here, going here, then what do I get? Well, what can we say this thing is equal to? It's what? So recall that if I start the relationship between what would be the mathematical expression for this guy then? It would be x of n minus n naught periodicized multiplied by r sub n of n. So that is the inverse DFT of this blah here, which is x of k e to the minus j 2 pi n naught k over n. And why is that? Well, because we already went through this. Because x of n, if I make it periodic, if I periodicize it, I get x tilde of n, which is just summation over k from minus infinity of plus infinity of x of n plus kn. And then I take its DFS, and then I get x tilde of k, and then I get x of k. And that's DFT, and that's DFS. So that's the relationship between DFT and the original sequence. And so what I'm saying is that if x of n was 0, 1, 2, 3, 4, x of n minus n naught, let's say n naught equals 2, is just going to be 0, 1, and then 2, 3, 4, 5. It'll be 0, 1, 2, 3, 4. And this can't be a valid inverse DFT of anything. So x of n minus n naught is not a valid inverse DFT. So instead, what is a valid DFT is the following. If you go through this set of pictures, is the following thing. So if x of n as a function of n looks like this, okay, then first I make it periodic. So I get x tilde of n. And then going through this chain that we just talked about, this is the chain I'm going through, right? Then I apply the shift property to this DFS, and everything holds true, so I get x of n minus x naught periodicized. So what would it be? It would be this, and this, and this, and this. And then I take one period of it, x of n minus n naught times r sub n of n. That's what making a period one period means. You just keep it. So it will be this, and then that. 0 to n minus 1. So this is what's called circular shift. So I shifted it to the right, but I don't let the shifted samples spill over in this region. They come back and wrap around in a circular way. Okay? So in the DFT domain, if you multiply by an exponential, it corresponds to a circular shift of a sequence. And how much is it shifted? N naught points. Okay? And I won't go over the proof of this thing because I think it's pretty straightforward. In the DFS, we already know that this thing happens. And proof of it in the DFS domain is extremely straightforward. Along the same lines, let's talk about another property of DFT that trips people off. So suppose I told you x of n has a DFT x of k. Now I make come up with x complex conjugate of n. What is its DFT? And your first instinct is to say, oh, I know how DTFT works. It's probably the same thing. In the Fourier domain, what do? I know none of you want to give the wrong answer because I already told you you're going to give me the wrong answer, but I give the wrong answer instead. What is it? The wrong answer is x complex conjugate of minus k. Because if it was x of n and x of omega, if I complex conjugate this, I will get x complex conjugate of minus omega, right? And you're tempted to say this is the answer, right? And the answer is no, that's wrong. Why? Because if this is an endpoint sequence that has region of support as a function of k, if x of k is non-zero from 0 to n minus 1, after I do this, x complex conjugate of minus k, it's going to have a region of support that goes this way. And that can be the DFT of inverse, that can be the inverse DFT, that can be the DFT of anything. By the same token, what do you think? So how do we resolve this problem? Same thing. Make this periodic. Go to the DFS domain. Apply the property properly in the DFS domain. Then take one period, and you get the answer. Okay. And so the answer should be what? So you start with. So let's call this y of n. We want to compute this. So DFT of y of n is just what? You start with the x complex conjugate of minus k. You make it periodic. This is the DFS thing, and I put a big hat over it to make it this periodic sign, and then I multiply by r sub n of k. So that's it. So each time you want to do this, write down the answer that you're inclined to come up with. This is what your intuition would have said. This is what the DTFT intuition would have told you. But just to prevent yourself from getting tripped up, make it periodic and extract one period. And this pretty much holds true, for all other sort of properties of this. And as an example, the symmetry properties. The symmetry properties are like this. So if x of n corresponds to x of k, then real part of x of n, again, what are you tempted to say, corresponds to the even part of x of k, right? But don't do that. put a periodic sign and multiply by r sub n of k and take one period. How about j times imaginary part of x of n? What would that correspond to? You're almost implied to say the odd part of x of k. But don't do that. Put a tilde on top and r sub n multiply by r sub n of k. That means you make it periodic and multiply by that. How about the real part of x of k? What would that correspond to? Again, you're tempted to say it's x of even a part of n. But don't do that. Make it periodic and multiply by one period, r sub n of n. And the same thing here, j times imaginary part of x of k. What's the inverse DFT of that? Again, you're tempted to say the odd part of it, but don't do that. Put the hat on and multiply by r sub n of n. Just so that you get things in the proper places. I'm going to stop now. What we'll talk about next time, having built all these machineries and thought experiments and all these other things, we're going to put it all together to talk about how we can use DFT to do convolution. And that'll be next time, Friday's lecture.